All right, DNS, DoT, DoH, what does it all mean? This is the last chance to leave for the RPKI talk. No, we're going to take a different take on this. So our goal with regard to this particular talk was to perform some measurements and see how things are being deployed. Now, I have to say up front, this is a very rapidly evolving field. As Paul just talked about, things are in discussion even now, and so things have changed a lot. So you have to take what I'm showing you today with a grain of salt in terms of where things are and where they're going, but at least does provide some insight into where we are in terms of deploying DNS over TLS, DNS over HTTPS, and something called TCP Fast Open, which I will get to in a little bit. Okay, so some of this is going to be a little bit of review, but for those of you that do not work in the DNS every day, this may be helpful, and so we have some visuals to go along with it. Okay, so we have three basic roles in the DNS. We have a stub resolver, which is typically a library on your computer that communicates with a set of recursive resolvers, which are typically fairly static, and then the recursive resolver, its job is to go out and find the answer from authoritative servers. Okay, so we have these three basic roles. And I should mention, it said on the previous slide, that DNS typically runs over UDP, which is connectionless. Now, there are many, and Paul just informed you of many of the dangers and insecurities with the DNS. I'll mention just a few of those here, but one of them is if you're on path, and this is actually isn't just UDP, this is also TCP, but if you're on path, then you can see everything that's going on. If you see packets go by, you can introspect those packets. By default, there is no encryption. But there's also some other things, because it's connectionless when using UDP, then it's also vulnerable to spoofing for reflection and amplification type attacks, and other related attacks, including cache poisoning that are off path. Okay, also, because it's clear text, it can also be used for filtering fairly easily. Think of the predictable port 53, where you can intercept things fairly easily if you wanted to, or drop packets, or do a number of other things. And also logging and collecting that data if you wanted to take advantage of that. So, you know, insert your favorite sort of mischievous character in the middle there. But also it could even go on the other side, as Paul mentioned, between recursive and authoritative server. So there are several places where this filtering or observation can happen in the DNS, and depending on your level of paranoia, you may be concerned about that or may not be concerned about that. But those are the things that we would be looking at in terms of characteristics that are inherent in the DNS that might be taken advantage of for malicious purposes. So just to mention a few items here, so often in terms of some categorizations, and these are sort of loosely categorized because there's some bleed over from one to the other. But Paul, I keep referring to Paul's talk because he did such a great job of outlining a number of different problems and solutions within the DNS, and one of those is DNSSEC, which is basically ensuring that an answer you get is correct no matter where you get it from. Okay, but it doesn't tell you much about, it doesn't encrypt your communications so that a passive observer could still get it. It just, once you've gotten it, once you've gotten it, then you can tell that it's legitimate or not. Okay, but we're not going to be talking about DNSSEC today. The other category is ensuring confidentiality. Okay, and again, there's depending on how you put these together, there could be some amount of authenticity as well, but I'm not going to distinguish a lot of that today. But in terms of this list, we have things like DNS over TLS, which I'll talk about more, DNS over HTTPS, DNS over DTLS, DNS over QUIC, and DNS crypt. Okay. DNS curve is not on my list here, but that was also an item that was mentioned in the previous one. But those are mostly about confidentiality and ensuring a connection between two parties as opposed to authenticating the data that you get no matter where you got it from. All right, but the subject of my talk today is mainly these two bolded ones, DNS over TLS and DNS over HTTPS. So let's talk about DNS over TLS. So this was standardized. Actually, the work goes back before 2016, but it was standardized in terms of the RFC that's in the IETF back in 2016. And so the idea is we use TLS to transmit a query. It's actually very much like the DNS over standard TCP, except now you're doing it over encrypted tunnel. Okay, and actually it turns out DNS over TCP is very much like DNS over UDP, except that you're adding a length header at the very beginning, a couple bytes to indicate length. Okay, so effectively what you're getting with DNS over TLS is a DNS query that's encrypted between two parties. But what you get then is you get some server verification. You can verify the server certificate to verify that the end host that you're communicating with is who you think it is. You could potentially do some sort of a client certificate as well, since this is TLS. Okay, and then once you've done that verification, everything between you is now encrypted. So if you're on path and you're observing this traffic, then it is no longer casually observed by the person that's introspecting this traffic. They can't decrypt it without the appropriate keys. It does use a dedicated port. Unlike the standard DNS, which uses port 53, DNS over TLS, or DoT uses 853. I can't bring myself to say DOT and DoH, I'm sorry. Okay, but DoT uses dedicated port 853. So as Paul mentioned earlier, it is something you could pick out just by, you could see that it's happening even if you can't introspect the queries, and you could block and filter if you wanted to, because a port is allocated specifically for DoT. Okay, so that's a breakdown of how DNS over TLS works. And just to sort of illustrate over here, because we'll come back to this in just a minute in terms of performance, if you think of UDP, standard UDP, and presumably one of the reasons why UDP was used in the initial DNS is because you send a single query, you get a single response, and it's a single packet exchange. So you go one packet out, one packet back, and it's one round trip time. Okay, but if you can see over here in the diagram, we have to do the full TCP handshake for a full round trip time, and then you have an exchange for TLS, for the TLS handshake, and then you get to the application data part. And so it takes a little bit more to, in this case, we've added 2 round trip times. And so there was some concern over that depending on how you use it. But overhead-wise, it can be more significant. Okay. All right, in terms of DNS over HTTPS, which was standardized in 2018, although there were some experimental instances of this before that, we're sending queries, and it doesn't have to be port 443, but most often is. That, again, does create some troublesome, create some worry for network administrators that can't tell the difference between this and other web traffic, particularly, unless maybe they know where it's going and they can block certain destinations. Okay, but it can be a little bit trickier in that sense. In this case, this is just a little example of how it might be used, where you're actually sending the wire message as the content of an HTTP post or as part of the query string in an HTTP GET method. Okay, and then you would receive it in the content of the response. It's base 64 encoded. But this is how it would typically go. And you have to be provided a given URL for this to work. Okay, there are some examples in the RFC for this, and actually in our experimentation later, you'll see that we used one of the examples in the RFC to discover when we were actually looking around. But really it could be specified however a server wanted. They would say, here's our URL that we are going to use for DNS over HTTPS. Okay, so this is a very, very brief comparison, not meant to be comprehensive, but again, you'll find that these are bleeding, and these, even within the last few weeks and months, have sort of changed. Traditionally, DoT, for example, was more system-wide and could be used for all applications with something like get, add, or info, but now we've seen that with the recent changes from Microsoft, for example, that's even a functionality that applies to DoH as well. So it sort of depends. Again, there's some a bleed over in these. I already mentioned this, but DoT follows the same paradigm as DNS over HTTP in terms of how it works. And then DoH is a little bit easier to implement at an application level. And one of the features of this, because now you're doing it in HTTP, you've opened it up to things like JavaScript, where you traditionally could only do, for better or worse, might I add. I'm not advocating one way or the other. I'm just saying that now you can do this over JavaScript potentially because you're outside of the realm of your traditional browser sandbox. Okay, again, we've already talked about the ports that are used, and there's some differentiation there. Okay, so let's get to our measurements here. We measured things from 3 different perspectives, and one of those was looking at resolvers. Now, because we wanted to do sort of a mass scale empirical analysis, the data set that we needed to come up with, we had to come up with a large set of resolvers. So the first thing we did was identify a large number of open resolvers to see. And so this is more like, for the intentional ones, this would be public DNS services. For the unintentional, maybe they're just something that they needed to close up. But here's what we ended up finding. So we queried every IPv4 address to see if it behaves like a resolver. And the way we determined it in our particular case, now I know this wasn't an open resolver study, this was simply to identify them. What we did was if we got a no error or an NX domain response, and the RA flag was set. So we wanted to sort of filter out the authoritative servers that were authoritative only. That's what we did. We got about 1.1 million servers that responded in that way. Okay, and then we also did a similar test to discover which of those resolvers, the subset of those that worked over TCP, which was surprisingly few, believe it or not. Then when we got to that point, we sent a query using DoT and DoH with the URL that I mentioned earlier. Okay, I'll talk a little bit more about that in just a minute. What we didn't have in this particular case was a IPv6 equivalent test. We didn't use an IPv6 hit list or anything like that to identify resolvers at this point. We were simply doing a scan for our data set. Okay, let's see. So that was, so in terms of looking at resolvers, so if you look at the highlighted portion of this, we were looking at initially the resolvers on the receiving end, who was able to receive DoT. Okay, so that sort of blue square covering the receiving end of the resolvers. And we found that there were about 0.15% of the resolvers, the open resolvers that we hit, that responded to DoT, so about 1,700. About 1,500 of those corresponded to the clean browsing group, and they all supported DoT, which was quite interesting. If we broke those down into autonomous systems, the entire 1,700, there were about 87 autonomous systems that had at least one resolver that was doing DoT. In terms of DoH, we found only 9 that responded. At the time, now this was pre-Google, Google was still doing their experimental work, so using the URL that we had, Google did not show up. Of course, they're a major player now as well. But all of the ones at the time, all the IP addresses at the time that we did the study were associated with Quad9 or Cloudflare. Okay, and we've done just a more recent study to sort of clean this up a little bit, and we found 35. So it's expanded quite a bit since we initially did the study. Okay, so now we wanted to look at, let's see. Hold on, where am I? Sorry, this getting caught up here. Okay, now we're looking at, there we go, at the TLS results for this. Okay, so we wanted to analyze the certificates on the server side and see exactly what was going on in terms of what we were, as a client, what we were being presented, since part of the idea of DoT is to have some assurance that the other side is who they say they are. Okay, so between the 1,700 resolvers that supported DoT, we found just 22 unique certificate signers. So GoDaddy and Let's Encrypt were the most popular among those. We also found 11 certificates that were self-signed, and we measured that by looking that the issuer matched the subject line in there. That's how we determined that they were self-signed. Okay, so there is some question about how much you really care about the client side being able to actually validate the authenticity of the certificate on the other side. Okay. Let's see, in terms of version support, we have the new TLS 1.3. Only about 4.5% of IPs supported TLS 1.3. And one of the neat features about TLS 1.3 is that it supports something called zero RTT. And remember I talked about that we go from 1 round trip time with traditional UDP to 3 round trip times. If you use zero RTT and something which I'll talk about a little bit later, which is TCP fast open, you can get things down potentially to 1 round trip time, which is really great. But only 4.5 of the IPs supporting DoT were actually implementing this. So there's some room for growth there in terms of deployment. Let's see. In terms of at least supporting TLS 1.2, which is not yet end of life, 1,700 or 97% of the IPs supported 1.2. That was good. And a few of them had turned off support for TLS 1 and TLS 1.1, which was a step in the right direction. So there were just 80 of those, and they actually coincided with the 79. There was an overlap there. Okay. Okay. So in terms of measuring support at authoritative servers, we also wanted to look. This was sort of the charter was initially the charter in the IETF was initially designed to look at stub to recursive encryption. But there's talk of expanding. I'm not sure where it is in that stage. I'm sorry, but there's a vision towards also encrypting between recursive and authoritative. And so we wanted to do a little bit of a survey to see where things were there and who was using it. So we started out by identifying our data set here as the authoritative servers for the top 5,000 Alexa sites and all of the top level domains. Okay, that includes country code top level domains, generic top level domains. And so this ended up being about 6,500 or so domains, and then the authoritative servers for all of those. Okay, and so, sorry, advancing there. Okay, so now if you look at the light blue box, that's sort of the area that we're now looking at. It's the recursive to authoritative side. So these are the numbers. We had about 6,800 unique IP addresses for the top level domains and about 10,000 unique IP addresses for the Alexa sites in terms of target servers. Okay, there was no instance in the TLD area of at the time we ran the survey in terms of using port 853 for DoT. No server responded on that port. However, there were 12 Alexa IPs that responded over DoT, and those were all owned by Facebook. Now, there was something in the news. This actually wasn't unexpected. Cloudflare had posted something a while back about encrypting DNS traffic between Cloudflare and Facebook, so this sort of matched what they were indicating. So it was somewhat no surprise, but they were the only ones that we did find. The domains themselves were all the Facebook domains, so it included Facebook, WhatsApp, and Instagram. I'm probably missing something, but some of those fancy apps. Okay, so let's talk a little bit about TCP fast open. So the idea behind TCP fast open was that, hey, it takes such a long time to do a handshake, and if you've already established a relationship with a server, couldn't you just speed it up the next time you talk to them? And this was important, not just, well, first it became important in the HTTP realm. Back in 2011, there was a paper presented at the CONEXT conference, and that first proposed this. And then TCP fast open was later standardized in 2014. But the idea behind it is, if you look at the diagram here, first thing that happens is when the client establishes a TCP connection, it sends an extra TCP option, the TCP fast open option or TFO option, and then the server responds in the typical way with the SYNAC, but it also includes that option back, the TCP fast open option, but it includes what we call a cookie. Okay, and then that client stores that cookie. They go through their communication and wrap up, and then the next time they communicate, so this would be the next time they communicate here, the client then sends, along with the SYN, they send some data, and the cookie. So in other words, payload data in the TCP packet associated with the SYN, whereas normally you don't do that. It's just to establish the handshake. What that means is, for a DNS query, if you have a cookie for a server because you have communicated with them previously, you can now send data immediately, and then the response can come back right in the SYNAC as long as you have the right cookie associated with that. So it reduces your round trip time in a normal TCP connection from 2 round trips to 1 round trip. Okay, and in the TLS connection, depending on what version, you either go from 3 to 2, or if you include the 0 RTT, you can actually go from 3 to 1, which is a great deal. So if you're doing a lot of different connections to a server using one of these newer encryption technologies, TCP Fast Open can be your friend. And so adopting it for the DNS was kind of a big deal, and it was involved in a lot of the research that came out for it. Okay. So the way we wanted to measure this, we wanted to measure this from 2 perspectives. One is by looking at the client to server realm, and we did this generically, looking at the regular DNS servers as well as the DNS over TLS servers. And so, but the way we did this, first, we sent a TCP SYN with the TFO option, and then we checked just to see if the SYNAC coming back also had the TFO option and a cookie that came along with it. The second thing we did was we actually, we didn't want to just say, oh, if we got a TFO option, then we should be good to go. We wanted to see, was it really actually working? Were they acknowledging our data when we used that cookie that they gave to us? So we sent 2 queries back to back. The first one requesting the cookie, the second one using the cookie, and we wanted to see if they acknowledged our data in the SYNAC. Okay? All right. So first thing we did, we looked at these same numbers of servers. We were first doing this in the authoritative servers. Okay? So let's see. We found that out of the TLD IP addresses, there were 11 that included the TFO option, and 10 of those were Google's. That's all. This is abysmally low in terms of this thing that's been about since first proposed in 2011 and standardized in 2014. Okay, and only 5 of those act data. And you might be wondering, what in the world? Why would you even send a cookie back if you're not actually going to use it, accept it later on? I'll get to that in just a minute. But there are some weird things that have to do with load balancing, okay, that are out there. Okay, so again, we found just 11 out of the TLDs. Out of the Alexa, there was a slightly larger number out of those IPs. So we had about 7.1% that sent the TFO option, and then only 18 that act data. Very interesting, right? So what we're finding then with TFO is that, at least in the Alexa, there's sort of this lukewarm effort to deploy it, kind of. and we're not sure all the reasons why we were seeing this behavior, but we did verify some of them, okay, where it sort of works, but you're not actually getting the advantage of it. Okay, so next we wanted to look at the root servers, okay? And the reason why we're looking at the root servers, if you look at my diagram down here, again, playing with TCP Fast Open requires the help of 2 parties. You have to be a client that supports TFO to take advantage of it, but the server on the other end also has to be taking advantage of it. It turns out you need support both in your OS as well as in your application. You actually have to write it into your code to use TFO. So it is a little bit involved. You can't just simply plug it in and make it work. Okay, so it's a little bit involved. But anyway, first, when I looked at the authoritative side, we were looking at which servers were supporting it. Then we wanted to look at which clients. So we have this wonderful set of data that we call the day in the life, or the diddle data, that is a 48-hour capture from queries that are going to the root server. In this case, groot was not involved, but all the other root servers, we got some portion of their traffic during 48 hours. So we had about 3.7 million unique IPs that queried the root servers over TCP. By the way, this is a shout out to DNS OARC, who collects this data. It is wonderful for us researchers to have a looking glass into what's actually going on the internet. Okay, so we had nearly 4 million unique IPs that queried over TCP at one time or another during those 48 hours. And if you can see, we had 89 of those clients that included the TFO option. Okay, and 32 of those included a cookie, but didn't send any data in the SYN. In other words, this time it was the client not taking advantage of the TFO. We have no idea why this is, and we're trying to figure it out in our lab environment why this was. And the other, it was sort of like shame on the server, you know, before when it wasn't responding, and we did find some behavioral reasons why that was. In this case, we have no idea why the client was not doing it. And we went back and studied this several times, sort of scratching our heads, did we do the analysis wrong? And in fact, we're able to verify that that's what we saw in the data. So this is our snapshot of the state of TCP Fast Open. Rest in peace. Okay, all right. So just in conclusion here, we've talked a little bit about DoT and DoH and some of the benefits that they offer, as well as some of the issues that we're encountering here. DoT adoption is limited, but does include some of the most well-known public DNS services, because that's what we had access to in our particular study. Okay, let's see, we're talking about, talked about DoH, this is sort of speculative, might surpass DoT in adoption, and then TFO is the last thing we studied, and there's some serious questions about its deployment. So that's all I have, and I'm happy to take some questions.
Andy Oxenrider from Nokia. I just wanted to make an observation. I've actually seen recently a new DNS resolver implemented in browser, though I think that one was using a Chrome native client and not actual straight JavaScript.
Wow. Okay. Thanks so much. Appreciate that.
Hi there, Glendine Comcast. So are you going to be redoing your study now that, especially around the DoH stuff, now that there's a growing number of DoH resolvers? I mean, Comcast has open resolvers, BT has open resolvers now, so they're starting to pop up all over the place.
Yeah, that's a great question, Glenn. And it turns out that we would love to. One of the things that we need to do, especially one of the limitations we had here, was that we were dealing with that resolvers that we could access, which meant they had to be open resolvers. The next thing that would be great is if we were, especially in the case of Comcast, and Comcast has been so good to work with us in the past in terms of providing access to otherwise closed resolvers, things that are open to their customers. But in terms of getting sort of a representative view, we would need other parties to help us do that, so we could get a view not only of public DNS services, but also of the different organizational ones. And this would be a great addition to this work and related work.
I will point out that while a lot of people are getting used to DoH and experimenting with it, that a lot of operators are providing their DoH servers as open resolvers currently. So ours are open resolver at Comcast, and I know BT's are as well, are open resolvers. So you have a window to play.
Okay, I was not aware of that. Thank you so much for the information. Yeah.
Martin Berry from Fastly. With the TCP Fast Open, you mentioned that you had some from the server side not sending data back.
Sorry, could you get a little closer to the mic? Sorry.
With the TCP Fast Open, you mentioned on the server side not sending data back that you might think it might have been load balancing, and not sharing the cookie amongst all the servers that are supporting a cluster. Were you able to communicate with any of the authoritative server operators to validate that?
Okay. Yeah, there was a little part experimentation. Let me tell you a little bit more about my experimentation, because I didn't have a slide on this sort of deliberately because we're still investigating this. But one of the places that we did our experimentation with in terms of TCP Fast Open, they had a single IP address that we're going to, and when you ask that IP address, let's say we gave it 1,000 queries. Out of those 1,000 queries over TCP, brand new TCP connections, there was a finite number of cookies that were, so we were actually able to see that they were load balancing to exactly 80 backends, and there may have been more backends, but at least in terms of TCP, they were just not being sticky in terms of subsequent connections. Now, that isn't the answer to your question. You asked, did we communicate with the operators? And the answer is we have casually conversed with the operators about that. We're sort of studying it just a little bit more because we want to find out what more we can learn about that from other operators that have similar configurations. And it's not really hurting anybody at this point, so it's sort of this anomaly that we want to take advantage of a little bit, not in a bad way, but in a measurement sort of way to understand a little bit. Anyway, that's the best answer I can give at the moment. You know, if it were something like a security vulnerability or something like that, then we'd certainly be on top of it and report that to them. But it's sort of a nuance that isn't really hurting that much. So we're letting it linger a little bit while we communicate with them. Is that a fair answer? Okay. All right. Any other questions? All right. Thank you very much. Appreciate that.